Download this code from codegive.com, link in the description below. OK, let's dive into Chapter 16 of the Rust crash course, which is likely focused on asynchronous programming, async/await. I'll provide a comprehensive guide with detailed explanations and code examples. Important notes ****Rust crash course. The exact content and structure of a Rust crash course can vary. This tutorial will cover common topics found in async Rust tutorials. ***dependencies ***, you'll need the Tokio crate for this tutorial. Add it to your cargo.toml file. Chapter 16, Asynchronous Programming in Rust, Async/Await. Asynchronous programming is a concurrency model that enables you to run multiple tasks concurrently without relying on threads. It allows a program to start a long-running operation, like reading from a network socket or a file, and instead of blocking and waiting for the operation to complete, the program can do other work in the meantime. When the long-running operation is finished, the program is notified and can resume processing the results. Why asynchronous programming? 1. Improved performance ***async programming can significantly improve performance in I/O bound tasks, such as network servers or applications that perform a lot of file operations. By avoiding blocking on I/O, you can use CPU resources more efficiently. 2. Reduced overhead * compared to threads, asynchronous operations often have lower overhead. Context switching between async tasks is generally faster than context switching between threads. 3. Concurrency without data races * Rust's ownership and borrowing system provides strong guarantees about data races, even in asynchronous code. This makes it easier to write safe and concurrent programs. Key concepts and syntax. 1. Async functions ***. The async keyword transforms a regular function into a function that returns a future. A future represents a value that might not be available yet. It's a promise of a value to be returned at some point in the future. Async functions do not execute immediately. They create a future that needs to be executed by an executor. 2. Await keyword ***. The await keyword is used inside an async function. It pauses the execution of the current function until the future it's waiting on is resolved, i.e., has a value. **await is what enables the function to yield control to the executor, allowing other tasks to run. 3. Future trait ***. The future trait is the core abstraction for asynchronous operations in Rust. It has a single method, poll, which is responsible for checking if the future is ready and either returning the result or indicating that it's not ready yet. You rarely need to implement the future trait directly. The compiler and async/await handles all of that for you. 4. Executors ***. An executor is responsible for running future s. It takes a future and repeatedly calls its poll method until the future is complete. The Tokio crate provides a powerful and efficient runtime executor. Common executors include Tokio, async std, and others. Complete example. Here's a complete example that demonstrates the basic concepts. Explanation * 1. Use Tokio time:\sleep, duration, imports necessary functions from the Tokio crate for sleeping, simulating work, and defining time durations. 2. Async fn task 1-i32 and async fn task 2-i32, defines two asynchronous functions, task 1 and task 2, that each simulate some work by sleeping for a specified duration. They both return an i32. 3. Tokio main. This attribute turns the main function into an asynchronous function and sets up the Tokio runtime. This is essential for running asynchronous code. Tokio main creates an executor that can run future s. For let future 1 equals task 1, and let future 2 equals task 2, these lines do not execute the tasks immediately. They create future s representing the eventual results of the tasks. 5. Tokio join, future 1, future 2, this is a very powerful tool provided by Tokio. It takes multiple future s and runs them concurrently within the same async context. The await on the join macro waits for all the future s to complete and returns their results as a tuple. This means both task 1 and task 2 will run at the same time, or appear to run at the same time, thanks to the non-blocking nature of await and the Tokio executor. Without Tokio join, you'd have to await each future sequentially, which would be less efficient. Common patterns and techniques. 1. Spawning tasks asterisk. You can spawn new tasks to run concurrently using Tokio spawn. This creates a new asynchronous task that runs independently of the current task. Tokio spawn returns a join handle, which can be used to await the completion of the spawn task. 2 channels, for communication. Tokio Sync MPSC channel and Tokio Sync broadcast channel are useful for communicating between asynchronous tasks. Channels allow you to send data from one task to another without blocking. MPSC, multi-producer, single consumer, and broadcast are common channel types. 3. Mutexes and semaphores Tokio Sync Mutex and Tokio Sync Semaphore provide synchronization primitives for protecting shared data in asynchronous code. These are essential for preventing data races when multiple tasks need to access the same data. These async-aware synchronization primitives are designed to work correctly in an asynchronous context. Don't use std sync mutex or std sync semaphore in asynchronous code. 4. Selecting between futures, Tokio Select. Tokio Select allows you to wait for the first of several future s to complete. It's useful for handling timeouts, cancellation, or when you need to react to whichever event happens first. Best practices. 1. Avoid blocking. The primary goal of asynchronous programming is to avoid blocking the executor. Never perform synchronous I/O or long-running CPU-bound operations directly in an async function. Use asynchronous versions of I/O operations, provided by Tokio or async std, and consider using Tokio task spawn _blocking to offload CPU-bound tasks to a separate thread pool. 2. Use asynchronous libraries when working with network or I/O. Use libraries that are designed for asynchronous operation, example Tokio, async std, request with the async feature, hyper, etc. 3. Handle errors as with all Rust code, handle errors gracefully. Use result and to propagate errors. Consider using tracing or log for logging. 4. Use arc for shared mutable state when you need to share mutable state between asynchronous tasks, use arc mutext or arc rwlock from Tokio Sync or async std, to ensure thread-safe access. 5. Be mindful of deadlocks avoid circular dependencies between mutexes. Always acquire locks in a consistent order to prevent deadlocks. Consider using try_lock to avoid blocking indefinitely if a lock is already held. 6. Experiment and profile asynchronous code can be more complex than synchronous code. Experiment with different patterns and use profiling tools to identify performance bottlenecks. Tokio provides tools for tracing and debugging asynchronous code. Debugging asynchronous code. Debugging asynchronous code can be more challenging than debugging synchronous code. Here are some tips. Logging use logging statements, println, tracing, log, to track the flow of execution and the values of variables. Asterisk tracing. Asterisk the tracing crate is a powerful tool for structured logging and tracing asynchronous operations. Tokio integrates well with tracing. Asterisk stack traces. Asterisk when an error occurs, examine the stack trace to understand the sequence of function calls that led to the error. Tools like backtrace can be helpful. Asterisk visual debuggers. Asterisk while visual debuggers, like those in VS Code or IntelliJ, can be used with asynchronous code, they may not always provide the same level of insight as with synchronous code. Pay attention to the asynchronous boundaries, example await points, when stepping through code. Advanced topics. Asterisk asynchronous streams. Asterisk the stream trait, from the futures crate, represents a sequence of values that become available asynchronously. Asterisk asynchronous traits. Asterisk you can define asynchronous methods in traits using the async trait crate. Asterisk custom executors. Asterisk while Tokio and async std are common, you can create your own executors for specialized use cases. In summary, asynchronous programming in Rust provides a powerful way to write concurrent and efficient applications. By understanding the core concepts of async/await, futures, executors, and synchronization primitives, you can build robust and scalable systems. Practice these examples, and experiment with different patterns to gain a deeper understanding of asynchronous Rust.